In this video, we look at Kempe's attempt to prove the four-color theorem. It was believed correct for over a decade until Heawood found a flaw. We will see exactly where it breaks down. We want to color every plane graph using only four colors. This is the four-color theorem. Every plane graph can be colored with at most four colors. First, let us recall two definitions. A plane graph is one drawn in the plane with no crossing edges. Here are two small examples. A vertex coloring gives adjacent vertices different colors. Watch the vertices fill in. No edge joins two of the same color. We are now ready to prove the theorem. To do so, we use the following lemma. Every plane graph has a vertex of degree at most 5. We argue by induction on the number of vertices. Take such a vertex V and remove it to form the smaller graph G'. By the induction hypothesis, G' can be colored with four colors. Begin with the easiest case, where V has degree 3. Remove V to form the smaller graph G' on the right. By induction, G' is four-colored. The three neighbors of V use at most 3 colors. So a fourth color is still free. Put V back and give it that color. This case is done. Next, degree 4. Again, we remove V and four-color the smaller graph G'. Now bring the colored neighbors to the center, around the empty vertex V. If the neighbors used 3 or fewer colors, one color would be free, and we would finish exactly as in the degree 3 case. This time, though, all 4 colors appear among the neighbors, so no color is immediately free. Consider the chain of red and green vertices that starts at the red neighbor. Suppose it does not reach the green neighbor. Then swap red and green inside the chain. The red neighbor turns green, red is freed, and we color V red. Otherwise, the chain does reach green. Together with V, it now encloses the blue neighbor. Trapped inside, the blue-orange chain at the blue neighbor cannot reach orange. Swap blue and orange there, freeing blue, and color V blue. Finally, the hard case. V has degree 5. If the neighbors use 3 or fewer colors, a fourth color is free, and we color V as in the degree 3 case. So suppose all 4 colors appear. With 5 neighbors, one color must repeat. Here, red appears twice. Take the blue-green chain from the blue neighbor. If it stops short, a swap would free blue. But suppose instead it reaches V's green neighbor. The blue-orange chain from the blue neighbor behaves the same way, reaching V's orange neighbor on the other side. Each chain together with V closes a cycle. The blue-green cycle walls off one red neighbor from the orange neighbor. So the red-orange chain at that red neighbor cannot reach orange. Swap red and orange along it, and the neighbor turns orange. In the same way, the blue-orange cycle walls off the other red neighbor from the green one. So the red-green chain there cannot reach green. Swap red and green along it, and that neighbor turns green. Now no neighbor of V is red, so we color V red. This looks like a valid proof. But is this argument really correct? Let us look more closely. But the two chains can look like this. Each one runs from the blue neighbor, up through the diamond, and around the outside. To free a color, Kempe swaps one of the 2 red neighbors, red-orange at one, red-green at the other. Case 1. Swap the red-orange chain. The red neighbor turns orange, and the orange vertex above it turns red. But now the red-green chain reaches all the way to V's green neighbor. Swap it, and the green neighbor turns red. Red was not removed, it only moved across. Undo everything and try the other order. Case 2. Swap the red-green chain instead. This time, the green vertex above turns red. And now the red-orange chain reaches V's orange neighbor. Swap it, and the orange neighbor turns red. Once again, red only moves over. Either way, red is never freed. It only moves to another neighbor. The two chains share a single crossing edge, so the first swap always breaks the second. This is the gap in Kempe's argument. Let us end in Kempe's honor. His 1879 proof was not correct, yet the idea was brilliant. It completely settles the five-color theorem, and his chains, now called Kempe chains, are central to Appel and Haken's 1976 proof of the four-color theorem. Thanks for watching. If you enjoyed this video, please like and subscribe to support the channel. More graph theory videos are coming soon.